Yeah, thank you very much for being here tonight. I know it's late for many of us. There's quite a lot to go through, so we'll be flying through a lot of these slides. And I try to keep them focused on mainly the challenges in dynamic environments. So what I'll be doing is to basically highlight what we learned from the LOCATA challenge in terms of dynamic environments, what the sort of issues are that we encounter. I'm trying to use a couple of approaches that we've meanwhile developed to address those challenges, but I'm probably going to be a little bit hand-wavy about the methodology due to the time constraint, and so I can focus on the challenges. So I provided the references for papers in the bottom, and by all means, please don't hesitate to get in touch after the talk if you have any questions. So the LOCATA challenge was an IEEE SPS data challenge that was aimed at localization and tracking approaches for acoustic sources. And specifically what we wanted to investigate was the limitations and the benefits of the approaches as we move away from the perhaps more classical scenario of a single static source towards the more realistic scenarios up to a point where we have moving listeners as well as multiple moving sound sources. So the scenarios really range over 6 different tasks, from a single static loudspeaker up to multiple moving human talkers involving a moving microphone array, well, actually several moving microphone arrays. The microphone arrays that we actually used cover a variety of geometries. We included a pseudospherical robot head that incorporated 12 mics, a spherical eigenmic with 32 mics, 2 hearing aids, so in total 4 microphones, so 2 on each side, that were installed in a head torso simulator, and finally a planar array that was quite surprisingly large. It's about 2 meters wide and included 15 microphones. In addition to the distant talking microphones, we also had close talking mics as ground truth information. So every human talker was equipped with a DPA mic that was very kindly taped to their cheeks so that we could extract information about the voice activity from each of the sound sources. The LOCATA dataset that you can obtain online, the link is below, incorporates both the microphone arrays as well as the ground truth from the close talking mics. So in the dataset, you have access to everything. However, participants at the time were only provided with the microphone arrays in the evaluation dataset. The recording was conducted in a lab room at Humboldt University Berlin, and the whole thing was a collaboration between Imperial College, Humboldt University, and Friedrich Alexander University in Erlangen. The reason we did it at Humboldt University was because that room is equipped with an optical tracking system, which was hugely helpful because it actually provided us with millimeter precise measurements of the ground truth positions as well as the orientations of each sound source and microphone array at 120 Hertz frame rate. So you get very accurate ground truth information at very rapid intervals. For evaluation, we computed a range of different evaluation measures. So in the paper, you'll find measures ranging from probability of detection and false alarm rates to track splits. What I'll focus on today is the azimuth error, but I'll show you in the plots what the sort of underpinning issues were that we were actually finding. For task 1, so this was for a single static source, we actually found really surprisingly accurate results. We were mightily impressed when we saw the results, considering that some of the approaches actually had down to 1 degree accuracy in azimuth error. And this is in a reverberant condition with ambient noise. So I think that is very worthwhile highlighting that this is quite a realistic scenario, barring the fact that this is a fully static scenario. For the hearing aids, both submissions resulted in comparable azimuth errors of around 8 degrees. This was somewhat to be expected, considering that the hearing aids have a substantially reduced number of microphones installed, and also that the arrays are, or that the microphones are affected by scattering and shattering of the head, which doesn't impact on some of the other arrays. Let's fast forward now to task 6. So this is involving moving microphones and multiple moving sound sources. So you've practically got a scenario that is very representative of real environments. Compared to the single source task that we've seen on the top slide, the results here are very clearly deteriorated, but more crucially, what really struck us at the time of evaluation was that only 2 out of 15 submissions even attempted to address task 6, so the fully dynamic environment. So very clearly, I think the takeaway story from this screen is there is lots of scope for future work within this space. There are very many opportunities, and what we were discussing today will be the underpinning challenges that we encounter in these environments that are preventing progress at the moment in this scenario, and some suggestions of how we may be able to overcome these issues. To this end, as an overarching overview, I believe that we can identify 3 main challenges that really hold back the progress in this area. Firstly, there's the impact of source motion, which leads to significant uncertainty. Secondly, we have the impact of competing sources, which requires robust solutions for source separation. And last but not least, we need to address the impact of ego motion, so the motion of the listener themselves. And the ego motion results in instabilities in auditory perception, but from perspective of localization, in very rapid changes in the reference frame between that we're using to observe this acoustic scene. So let's start with source motion, have a closer look here. What we observed in the LOCATA challenge is that when we move from a fully static single source scenario in task 1 to a single moving source in task 3, we actually observed a drop of a few degrees in performance. This is particularly noticeable in the significant increase in the standard deviation for each of the submission that is reflected here by the error bars. So even though the average averaged over the number of recordings per task, did not necessarily result in a substantial or a shocking degradation in the performance, the standard deviations did somewhat explode. Really, the impact of the source motion on the localization error, on the localization accuracy, is down to several issues that I'd like to go into a little bit deeper here. And one issue is that auditory perception in dynamic environments is subject to variations across both time and space, as the sound source relative to the listener is actually moving. So let's assume, just to illustrate this, that we have a source that moves at a constant speed of 1.4 meters per second. So this is average human walking speed, along a radius of 1.5 meters away from the listener. Then in this scenario, the source direction changes by 53 degrees within a second, or by 5.3 degrees within even a 100 millisecond block. So these are quite rapid variations that we somehow need to compensate for. So clearly, given the rather rapid variations in the source directions, we're no longer able to take the more classical approach of a long recording that can be processed in one long batch to get as much information as possible out of the data, but instead we need to process the signals sequentially using short blocks of data that we slide along. And each of these short blocks is then used to provide us with an instantaneous estimate of the source direction at that particular snapshot in time, and independent of the past or any future information. The problem with that is that when we deal with very short snapshots in time, that, of course, these are very severely affected by source inactivities, which naturally occur during speech. So what we actually need to trade off is the duration of these blocks and therefore the variation of the source position within that time span against the possibility that there might be elongated periods of source inactivity. So overall, what can happen is that voice inactivities can actually either lead to outliers and false detections, for example, in blocks where we have no activity at all, or in blocks where we have a mixture of some voice activity, some silence, to actual biases or to an actual bias in the estimator. To illustrate the need for for detection of voice activity periods when dealing with this type of data, particularly when we want to deal with streaming data, let's have a look at a concrete example here. So what you see here as the solid dark blue line is the trajectory of the source azimuth relative to one of the microphone arrays in the LOCATA dataset. And the gray shaded areas indicate periods of voice activity. The orange line corresponds to the azimuth estimates obtained by submission ID 6. And while this particular algorithm works extremely well during voice activity, there's a significant number of false estimates during periods of voice inactivity. I should note at this point, during the LOCATA challenge, we did not penalize against these voice inactivity periods, and we also taught that to our participants in advance. So participants didn't have an obligation to actually apply voice activity detectors, but some of them did regardless because they wanted to test their systems. So we excluded those periods from the evaluation, but it's nevertheless interesting to observe that here, what the impact of voice inactivity actually is on signals, if not carefully taken care of. So naturally, these issues can be overcome by pre-processing the signals using a voice activity detector. For example, you could very simply monitor the received signal energy compared to the ambient noise level. It's mildly questionable how well that will work in realistic scenarios, but you could try it regardless. And such an approach of applying voice activity detection was actually taken by submission 7, which is shown in blue here. And what we see here is that actually submission 7 very drastically removes, for obvious reasons, those outliers during voice inactivity, clearly because their voice activity detector seems to work rather well. However, there still appears to be a slight issue. There's a delay in the onsets of speech where the detector hasn't quite picked up on it. And there's also a delay in the offsets. This particularly affects tracking algorithms that we'll go into later on, where basically tracks keep being propagated up to a certain point where you then cut off the track and terminate. But it's worthwhile noting that even though voice activity detector may help the situation, you still need to make sure, if you need highly accurate results during onsets and endpoints, that those are properly accounted for. Another issue that we face is that so far we've considered treating each window in isolation. However, of course, the positions of a sound source along a trajectory are highly correlated across both time and space. So by looking at these data blocks in isolation, we're actually throwing in vital information about the past as well as the future that, well, not so much of the future in the causal system, but definitely the past that we could exploit constructively in order to actually smooth out our data. This becomes particularly problematic in scenarios where we have low signal to noise ratios, where our instantaneous estimates are actually subject to significant estimation errors and therefore often result in outliers. Perhaps more importantly for people who work in robotics and autonomous systems like myself, treating data blocks in isolation is completely prohibitive for long-term memory and situational awareness. So if you want to do spatial mapping for long-term memory to actually provide your AI with contextual information, treating things in isolation will render your robot entirely memoryless. So the question now becomes, how can we integrate past information in a meaningful manner? There is significant evidence from the neuroscience community that human experiences are actually shaped through anticipation of outcomes and then subsequent correction of these predicted results using sensory information. And that's actually quite an interesting concept that very well aligns with the Bayesian paradigm, and particularly Bayesian online learning. So from a Bayesian perspective, our aim of source localization, or actually source tracking in this case, is to infer the posterior probability density function that describes the direction of arrival of a sound source. And crucially, because we're actually estimating distributions or density functions rather than point estimates, Bayesian inference enables us to actually quantify uncertainty in our belief. Again, for roboticists and for people working in autonomous systems, this is hugely important because ultimately what we want to do is to make decisions based on our estimates. To make decisions that are based on uncertain estimates, we need to evaluate risk. And as such, we need to be able to quantify uncertainty to gauge that risk. So actually having a mechanism in place and a framework in place that naturally allows us to quantify that uncertainty is hugely beneficial. So now let's assume that we at time t we have an estimate of the previous, so t-1 distribution in place. So we have a past posterior that is highlighted in the red box here, and this posterior density for most distributions can be described by some kind of mean or location. So in this case, mu t-1 associated with a covariance. So in this case, sigma t-1. And this covariance quantifies this uncertainty in our prior belief. Let's also assume that we have a stochastic model of how our source actually behaves in space. Then we can describe this model as a transition PDF and apply this transition PDF to our past posterior in order to make a prediction. So this new predictive PDF is again characterized by a mean mu t given t-1 and a covariance. And you will note that compared to the past posterior, the covariance actually increases. And this is because we're actually just extrapolating information based on prior belief rather than actual factual evidence or sensory evidence. So we would assume that our uncertainty therefore must increase because we have no evidence left yet. Of course, we then obtain our next data block. So once we have our next data block, we can describe the distribution according to that by a likelihood function, which is again characterized by a mean, and this time a reliability of that particular measurement. And we can now apply this likelihood function to update our belief in the predictive PDF in order to obtain an estimate of our current posterior PDF. So ultimately, we now have a reduced covariance or a reduced uncertainty due to the fact that we're now actually using sensory information to update our belief. So this is how you can actually incorporate information within a Bayesian framework to smooth out the results and to make sense of long-term dependencies in the system, in your long-term dependencies of sound sources. One thing that you will note here is that I've assumed here that this is for a single source only. And this leads us to our next problem, which is competing sources. So any of the problems that we've seen in the past slides are actually exacerbated in scenarios where we need to deal with multiple competing sources. The reason, as most of you will be very well aware of, is that the fundamental problem is that sounds of each acoustic source in the scene are actually compressed into a single waveform at each microphone installed on board of our listener or our robotic system. So we actually need to address a source separation problem here whilst simultaneously trying to make sense of this continuously changing world, which is obviously a very, very complex problem. As a consequence, what we observed in the LOCATA challenge is that out of the few approaches that even attempted to address the task involving multiple moving sources, so task 4, the performance actually dropped quite substantially, in some cases leading up to errors of over 20 degrees. So there are significant challenges in this. From those results, you would still think, well, most of those approaches still have under 10-degree azimuth accuracy. That looks good to me, until you look at the close things. So what we actually observed was that whilst most of the approaches had very accurate instantaneous estimates, the coherent integration over time was where most approaches really fell down. And this is also where most of, I believe, where there's a lot of scope for potential work in it. So clearly, because most of these approaches have only accounted for spatial information, we noticed that the spatial information or spatio-temporal information alone actually leads to ambiguities in the source identity. And specifically, we observed that there was a significant number of swaps in the track identities as well as broken tracks. So there were sort of short periods where there's probably quite a dominant signal, where the approaches would very well pick it up and nicely track through, and then the track would be broken due to perhaps a drop in signal energy. And at that point, there was that ambiguity of which source is actually taking over. And that is really impacting on most of the approaches that were submitted to the LOCATA challenge. Of course, an obvious question could be, and I believe this was actually asked earlier on, about exploiting male and female speakers to disambiguate between a masker and a target. Why do we actually constrain ourselves to purely spatio-temporal information for localization and tracking when, in actual fact, audio signals encapsulate a wealth of spectral cues? This was not part of the LOCATA challenge, but in recent work, we started to investigate the use of voice pitch as personally identifying feature that enables segmentation and separation of overlapping speakers. So Aidan Hogg at Imperial is investigating how we can use voice pitch and our fundamental frequency to disambiguate scenes involving multiple overlapping speakers. Specifically, we're utilizing Bayesian approaches to track the fundamental frequency of multiple speakers and thereby identify speech onsets, endpoints, and overlap. And what that enables us to do is ultimately to estimate also the number of simultaneously active and competing sound sources. The thing is that while our results at the moment can very accurately distinguish between, for example, male and female speakers, of course, there is still ambiguity in the voice pitch between speakers who have very similar voice pitch. So, for example, two males in the same depth of voice would still result in some level of ambiguity in this approach. Nevertheless, the use of spectral cues in addition to spatial cues is highly beneficial to disambiguate in scenes that approach the cocktail party scenario. Fundamentally, therefore, the problem that we need to deal with is that the number of sources itself is actually the key problem. Mainly, we don't know the number of sources a priori, and therefore the number of sources as well as the source states themselves are actually subject to uncertainty. And we very clearly noticed this in the LOCATA challenge. So this is a submission for task 6. So this is the complete problem, multiple moving sources, moving microphone array. And what we saw here was a very significantly large number of tracks, in this case up to 7 tracks, that keep swapping, whereas actually we only had 2 sources in the scene. And what's normally happening is that people assume, or the algorithms assume, or are based on the assumption that the number of targets is limited to a maximum number. For a tracking algorithm, what that means is that it will sort of run through the tracks up to the point where it hits that number, and then basically loop through or something like that, or try to associate similar things with existing tracks that are already on the fly. The challenge, though, is that that is not necessarily a realistic assumption, because, as I mentioned before, from a probabilistic point of view, actually the number of sources themselves is subject to uncertainty. So rather than modeling our joint PDF of the set of sources as a product of statistically independent sources, we need to deal with a random set of sources where the number of the sources as well as the states are unknown. And what that means is that at every time step, we actually need to explicitly enumerate all hypotheses that there might be no source at all, there might be a single source, or there might be any combination of previously active and newly active sources in the scene. So very clearly, the key problem here is this term that actually loops over the set of partitions, and therefore this is a hugely combinatorial problem and therefore analytically intractable. Luckily for us, point process theory actually deals with random sets, and it actually enables us, provides us with a mathematical framework that allows us to approximate this term and therefore allows us to devise Bayesian models for multi-source tracking. So if you're interested in point process theory and multiple sources, please do feel free to read those papers below. Shameless advertising, apologies. Right, so far, what we assumed was that we're dealing with static listeners. So far we've assumed that we're dealing with static listeners. Sorry, I got confused there. However, naturally, our listener as well as our sources are moving. Even whilst I'm sitting here, I'm constantly rotating my head, and those even subtle head and body rotations have a significant impact on my auditory perception. For localization, what this means is that actually the reference frame of the listener is continuously changing, so that the position of a sound source relative to the listener changes, even though the source may be static. So the impact of this ego motion is perhaps best illustrated using an example from visual processing. So what we see here is a recording from a stereoscopic camera, where a robot actually looks in the direction of an active speaker. And if you focused on the speaker in the brown t-shirt who was on the left a moment ago, the robot shifted its focus to the person in the striped shirt. And as such, the relative location of the speakers to the robot keeps substantially changing, even though the speakers remained roughly in the same positions. So the impact of these very rapid variations were actually reflected in the LOCATA results by quite severe degradations in the localization results. So for task 6 involving multiple moving sources as well as a moving listener, both approaches result in up to 16 degrees error compared to the sub 5 degrees for task 1 involving a single static source. And clearly, to make sense of these scenes that are now rapidly varying, we need to compensate for the ego motion of the robot. While there is a relatively large body of work that addresses the stabilization of auditory perception for human listeners, the problem from a localization point of view still remains that we need to perform these reference transformations in order to compensate for that motion. So effectively, at each point in time, what we need to do is to readjust our local coordinate frame to actually reapply the coordinate frame to some reference point or some reference orientation. The problem with this is that for reference frame transformations, we require an accurate estimate of both the source direction as well as the distance that is relative to the sensor. The problem is, for compact microphone arrays, it is very difficult to obtain accurate estimates of the source to sensor distance, and as such, we cannot perform these reference to frame transformations in closed form for listeners that are subject to rotations as well as translations. One approach that we've investigated, and a similar approach was actually submitted to the LOCATA challenge as well, was that we literally decided to flip the problem on its head. So the idea is, why don't we interpret the motion of a robot in the environment as a rotation of the environment around the robot. So in other words, the robot motion translates into a rotational velocity of the source, and rather than having to perform explicit reference frame transformations, the rotational velocity can now be absorbed in a model of the source dynamics. Apologies for the switch over there. So we can actually absorb this motion of the machine, assuming that we know how the machine or how the listener is moving, into the prior PDF as an uncertainty of our dynamical model. And within the Bayesian paradigm, we can then still predict the source position as before, which is a very neat, very handy and neat approach. But of course, it suffers from the limitation that we are actually adding more uncertainty in our system. So our risk is therefore increasing, and this makes our estimates for decision-making less reliable. And then finally, as Alistair alluded to in his conclusions earlier on, to stabilize head rotations, head tracking information is required. Indeed, in the LOCATA challenge, we actually provided participants with millimeter precise ground truth of the source and microphone positions, as well as their orientations. However, in practice, this is not always a realistic assumption, particularly the position. While some devices are equipped with inertial measurement units, accelerometers are subject to drift, and as a consequence, it is not possible to coherently integrate information over long observation periods. Now, admittedly, this may not be a problem for conventional hearing aids, where perhaps we're often only interested in relatively short-term memory where the drift is not substantial. However, for robotics and autonomous systems, long-term memory is crucially required to ground, for example, language and context, and especially since linguistic cues can often occur out of sequence. So it might be that a speaker is actually referring to an event that has happened a few minutes ago, in which case we need to have an appropriate memory span in order to be able to ground this information in actual context. In practice, what we therefore need to do is to estimate simultaneously the set of source states as well as the robot state or the listener state. And I will now refer to a robot, since this is mostly a problem for robotics. We need to estimate these variables from the audio data that we have, but we do have access to IMUs, as I mentioned, although these are subject to drift and therefore uncertainty in themselves. And this problem of self-localization and mapping is actually known as SLAM, so simultaneous localization and mapping. It is well known that the SLAM problem can be separated into, so the joint PDF of our set of source states as well as our robot position can be separated into the marginal PDF of our robot that is independent of the sources, times or multiplied by the PDF of the set of sources. The problem that we have here is that a standard assumption in the SLAM community is that this set of source states can be separated into a product over the statistically independent individual source states. And as I mentioned before, that is not necessarily a valid assumption if we don't know how many resources we have, which is a problem in audio, and a very audio-specific problem, in fact. So as I mentioned before, we can actually separate our PDF into these terms here, which then leaves us with a combinatorial problem. However, using point process theory, what we've shown is that this actually reduces to these two strange terms here. And what they are is actually the belief that one of the many sources takes a particular state in space, and the likelihood of a given detection of a source given the robot state. What this means is that effectively we're actually anchoring our robot using detections, instantaneous detections of the source locations that we're using. So what this means, because we have a product over all these terms, any detections where none or only a small number of detections align with the sources will very rapidly drop to a probability of 0, such that only those detections that align well with our source, with our predicted source states, will obtain a sufficiently high probability to become stochastically meaningful. And we've shown that with those assumptions, that we can actually self-localize a robot within reverberant environments with rather high accuracy. So to summarize, The challenges that are impacting on machine listening in dynamic scenarios are quite diverse. Some of the challenges boil down to source motion, competing sources, and ego motion. I didn't quite go down the rabbit hole for each of those. I could probably talk on for hours about this, but the main issues that you might want to start thinking about if you've never dealt with dynamic sources before or dynamic scenes before are spatio-temporal variations that prohibit us from actually performing batch processing, source inactivity that can bias our estimates, overlapping speech, which results in ambiguity in the source identities, and uncertainty in the number of sources that results in a combinatorial problem. And of course, we somehow need to address a problem where we have a missing source sensor range so that we can actually deal with reference frame transformations appropriately and in a tractable sense, as well as an unknown self position, which is highly prohibitive for coherent integration of long-term memory. Thank you very much for your attention. If you have any questions, I'd be more than happy to answer them now, and please do feel free to get in touch.